So summarizing the last example, for this MOSFET amplifier, we determine the DC voltage gain and loop gain through taking the small signal circuit, generating the signal flow graph, and applying Mason's rule to determine the transfer function or voltage gain. And so the voltage gain is then equal to 9.42, which is consistent with the textbook. And at the same time, we've also determined the loop gain, because the loop gain is in the determinant, just this expression here. This is our loop gain, CD, E, F, G. That just represents this loop going, that's our loop, and the loop gain is 16.35. 16.35, and I'll neglect the minus sign because it's understood to be a negative feedback circuit. The final requirement for this question that we need to answer is the output resistance, R out. So just thinking back again, what that means is if we had we're trying to determine the output resistance looking into the output terminal. So that's almost like if we had a curtain hiding the circuit. If we could determine what that output resistance is, it would be the Thevenin resistance looking into this circuit. And this being an amplifier, it's dependent on the input voltage, VI, and there's some gain times VI. So if we want to determine the output resistance, the classic approach that you learned in ECE 212 is to set the input equal to 0. If we do so, then that would turn the dependent voltage source to 0, and that would leave us looking in to just seeing R out. And then to determine the output resistance, we would apply a test signal. In this DPI SFG analysis, the easiest would be to apply a test current and then to measure the resulting voltage at the output. Or we could just write V out over here. And the output resistance would therefore simply be the ratio, it's defined as the ratio of the resulting output voltage for a given test input current. So V out over I test. So we can just go back to the circuit then and apply this test current I test onto this circuit. Now the reason why we are using a test current for DPI SFG analysis is because it makes a trivial change to the signal flow graph. So we notice here the introduction of a current I test into the output node simply means that there's an additional short circuit current component this is the output voltage, so there's the short circuit current. We're simply adding a test current, an additional test current to the short circuit at the output. So this would then be, we would add a node, this is I test, and now we are going to inject that, so it's just a coefficient of 1, into the node. All right, and the output resistance is simply then V out over I test. So now our transfer function is from here to there, and if we want, we can say that V out is V in, sorry, is equal to 0. So that doesn't, the input is now from here, and we can ignore that. But basically, we have the same signal flow graph, and so Mason's rule would allow us to determine that this transfer function is equal to P1 delta 1 over delta, where P1 in this case is simply 1 times G, and again, if we remove that, then we have no more loops, so the delta is simply 1. And the determinant we've already calculated. This is the same signal flow graph, so it's 1 minus L, and L is the same. And so we can simply plug in the values, G being 4.7 kilo ohms, and 1 and L was 16.35 negative, and so that equals to 272 ohms. And this again is consistent with the result from the textbook, and we can write 272 ohms. So as you can see, there really is very little work to solve the last two parts. By calculating the voltage gain, we already obtained the loop gain, and it's a simple change of the denominator essentially to determine the output resistance.